Cool. So once again, welcome everybody. Um, this is for the second midterm, which I believe goes from, what is it, linear independence? It goes from, yeah, linear independence all the way through invertible matrices. So you won't have to do any kind of like determinant stuff from there. But to know how to do determinants still will help you with things like invertibility. Okay, so what questions do we have?
Um, for sample midterm A, did you go over problem 7, part B with the graph?
Yes, 7B midterm 2A.
Yes.
Got it. Give me 1 second to screenshot it and get it over here. Cool. So what we're looking at here is they give us a two-dimensional graph with 2 lines on it, and they say one's the column space and one's the null space. How do we go backwards from this to tell us what the actual matrix is, or what a possible matrix to create these two spaces is? I'll start this generally by making, well, let me write out what column space and null space are first. So column space of A is just our new word for span of the columns of the matrix A, which obviously you can see why we want to abbreviate that. So this is just our new word for span of columns. And this has the same shape as we talked about for the first midterm, which is number of pivots, dimensional in R to the number of rows. And likewise for null, A is our new word for solution set. 2AX equals 0, or the homogeneous solution. And the shape will still follow like we have for our solution sets before, which are number of free variables, dimension in R to the number of columns. Okay.
Sorry, what do you mean by shape?
Like the column space is a plane in R3 is like what the shape would be. So in this case, the column space is a line in R2. Does that make sense?
Yeah.
Okay, cool. So in this particular case, we have a column space, which is a line in R2, which tells me that I have 1 pivot and 2 rows. And then for my null space, which is also a line in R2, this tells me I have 1 free variable and 2 columns. Cool. So from here, the big thing to look at immediately is that we have 2 columns and 2 rows. So we're going to have some matrix that's going to look like this. 2 by 2 with A, B, C, and D. Okay. And now we actually need to start looking at the graph. I usually just pick 2 points that I think are easy. So I'm going to pick this point and this point. Okay, and we'll get back to each of them in a moment, but we'll start with the column space. So for my column space, it's equal to the span of whatever that vector is, which is -1, 4. Okay, so this is the span of my columns of the matrix A. So this means each column has the shape -1, 4. So it can be -1, 4 is one column, +10, -40 is one column, -2, +8 is one column, any combination of these things, but they all must have the same kind of multiples like that. So this tells me calls shape, that's not how you spell shape, of -1 times some number 4 times the other number. 4 times that same number. Okay, so what does that mean for this matrix over here? Well, instead of writing A, B, C, D, and remember that this is the same thing as positive 1, negative 4, we can write this as negative 4A, and for B, we get negative minus 4B. Cool. So we just went from 4 things we don't know to 2, which is a nice step up. All right, any questions on how I did the part of this with column space?
Yeah, I didn't quite get how you got how you multiplied it by -4. Like, if the column space is the span of -1 and 4, why does that mean that you're multiplying by -4 in the bottom parts?
Because since these are like the span of things, this is just the same thing as saying it's the span of any constant times that. So it's the same thing as span as 1, -4. So another valid thing we could have done was we could have also just made this negative A positive, negative B positive. Okay, it's the same thing. They just have to have this general shape multiplied by any number. Does that make sense?
Yeah.
Okay. So I'll go through all of this, how to do it generally, and then I'll do this problem over again when we just plug in numbers. So that's how we use the column space to get some information. Now we're going to use the null. And null is the span of, in this case, it is 2, 1. I'm actually going to pick a different point. I'm going to pick this point over here. Of -4, -2. Okay. So this is my vector in parametric vector form, right? So how do we go backwards from this vector to a matrix? Well, what I mean by this is a vector in parametric vector form is you'll have something that looks like this, right? But there's a problem with how this is right now. And that is if we rewrite this as x1 equals -4 times x2 equals -2 x2. So this obviously isn't something we want because the only solution to that is 0. So what we do instead is we multiply this by some number, okay? And what that number does is we make this equal to 1, okay? So in this particular context, the C is equal to -1/2, okay? So this is parentheses. We don't like this. Instead, we're going to write this as times x2. And now we're going to multiply what we had by -1/2 to get +2, +1. In this particular case, it's easy because we can just pick it off the graph. But what you really want is you want this number, this bottom number, to be 1, okay? So now let's take it from these vectors back to where we can use them in a matrix.
Why do we need the bottom number to be 1? Like,
because looking at this right here, if I look at the equation for the bottom row, we have x2 equals -2 x2. And that's not how we write free variables, right?
yeah.
We need this to be x2 equals x2. So I just do that by multiplying both by -1/2. Does that make sense?
Yeah.
Cool. So from here, get x1 equals 2x2, x2 equals x2. I'm just doing the process backwards from how we would find this usually. So we rewrite these as x1 minus 2x2 equals 0. And that bottom equation gives me nothing because that's just 0 equals 0. And we subtract. So what this tells me is in REF, all rows have form 1, -2. Okay. So that means all of my rows, if the first number is 3, the second number is -6. The first number is -1, the second number is +2. The first number is 5, the second number is -10. If the first number is 1/2, second number is -1. Okay, these are all possible rows given that this is the null space. All right. So far, so good. Okay.
Yeah.
So from here, we're going to rewrite this matrix we had before. So we had minus A, 4A. And we had minus B, 4B. Okay. But now we know that every row must have the form 1, negative 2. We can rewrite this as minus A plus 2A, 4A minus 8A. Okay. So from here, everything's in terms of A. So we just pick some A that we want, and we just fill this matrix in. Minus 1, positive 2, 4, minus 8. And that's how you would solve a problem like this.
Wow.
Wait, I have a question. How did you know the B was 2A?
What we knew was we knew the rows had to have this form. Okay. So we didn't necessarily know what B was, but we just knew that the row has to look like that. Okay. So essentially we just kind of got rid of this and wrote the rows in terms of the first one because it has to be true based on the null space. And another way you can check that we've done this correctly is the second column should still have that form of a multiple of minus 1, 4, which it does, times negative 2, right?
Okay. I have a question.
Yeah.
Why do we know that from the null space we get the number of free variables in each column? And how do we find, like, how does the null space give us that information? Like,
so what the null space tells us is it tells us this vector when we're in parametric vector form.
yeah.
Okay. And if it tells us this vector, it's the same thing as giving us this equation.
It tells us the number of free variables.
Yeah. It does, but that's the important thing here is the numbers we get from that because we have one free variable. Okay.
Yeah.
So we can get that equation from that vector. And from that vector, we can get what our rows would look like. And from knowing what our rows would look like, we can get a generalized matrix.
Okay. Yeah.
Does that make sense?
Yeah.
Okay.
I'm still a little confused. Like, where did you get the 2 and minus A?
The 2 and the minus A?
The minus 8. Like those two. Because like,
That's
yeah, because like I understand the minus 1 and 4, but on the 2 and minus 8.
Yeah, so you can think that column space usually has to do with appropriately named columns. And then null space has to do with rows. So knowing that our rows have the form positive 1, negative 2, that tells me that whatever my first number is, the second number is going to be negative 2 times that. Okay. So here I knew what my first number was, negative A, and we multiply by negative 2. Same thing here. Does that make sense?
Yes.
Okay. I'm going to do this as well with numbers, which the process is a little bit simpler because we're not using any variables and we'll just get a matrix. But any other questions on this?
I had one question about just going back to recap how we got our first numbers from the graph.
Yep. Okay. That'll actually be easiest to show when I solve this with numbers. So I'll go ahead and do that. Okay. So all we need to do is we need to pick numbers that look easy. So I'm just picking 2 points. Okay. And what I'm going to do is I'm going to pick 2 different points. I'm going to pick this point. I'm going to pick this point. Okay. This one being in column and this one being in null. All right. So if you want to make this a little bit easier on yourself, one thing you can always do is take a vector from your null space and make it your first column. Okay. 1, negative 4. That's this point. Okay. Now we have half of a matrix. Cool. We're 50% there. Okay. What this is doing comparatively to how we solved down here is I'm not picking an A, I'm just setting it off the bat. okay? And in this case, it happens to be 1 just based on the vector I picked, but it's not always the same case. Now we have to do the same sort of thing with our null space. Should be the exact same process. We have the vector 4, 2. And to make this positive 1, we need to multiply by 1/2. So this gives me 2, 1 for my vector again. So this is solving for my null space now. X vector equals x2, 2, 1. x1 equals 2, x2, x2 equals x2. And from here we go to our equations where we like our variables on the same side. And then from here we just take the coefficients to get what our matrix would look like. So my first number is 1, my second number is -2. Okay. So now we have one more spot to fill. Okay, there's 2 ways to do it. To do both is to know you've done the question correctly. All right. Number 1 is to go from here to here by multiplying by -2. And the other is to go from here to here by multiplying by -4. And if we've done this correctly, we should get the same number. Okay. Any questions on this?
I have a question.
Yep.
So I see that you wrote everything in terms of x2 because that was the free variable. So what happens when you have x1, x2, x3, like a situation like this? Like how would you write the free variables?
You would just have to pick x2 or x3, whichever one you want. You should, in general, you should pick the lowest variable. So like x3 is the lowest on like my x vector. But you won't be expected to do that on the exam because we're not going to give you a 3-dimensional graph and ask you to take points.
Okay, cool.
But that's how you would do it. It would be exactly the same. You would
Would I
just
have
write
to
it as
do
like
it twice,
x3.
like for each free variable, x1 and x2 and x3?
If they just gave you a line, then it would just be one vector. That's a more complicated question, but I wouldn't expect the same thing like that on the exam.
Thank you.
Cool. Yeah.
I had another question.
Yeah.
Yeah. So why would you know to multiply, like when you have like -2 that you'd multiply by -4, or like a -4 you'd multiply by like -2 to get like that 8 value?
So this -4 comes from my column space because all of my columns have the form of 1, -4, right? So to get from one to the other, we multiply by -4. The other comes from my null space, which talks about rows. So I go from 1 to -2 by multiplying by -2.
Oh, yeah.
Does that make sense?
Yes.
Cool. Anything else? Okay. There's a question in the chat, which I'll go ahead and say out loud. How will the invertible matrix theorem be helpful? Let me actually check something real quick. Yeah, so the invertible matrix theorem, all this is saying is like, if a matrix is invertible, the big thing that you need to understand is that you can talk about transformations and how you would undo them, which is maybe more intuitive sometimes than others. Like if you're rotating 45 degrees clockwise, to undo that, to do the inverse, is to rotate 45 degrees counterclockwise. Yeah. The big thing to get out of that that's probably most relevant to this exam is that something that's invertible has to be both onto and one-to-one and square, which is another way of saying that if it's invertible and you row reduce it, you'll row reduce to the identity matrix for a square matrix. Okay. So that's useful to know for a few different things. For instance, a common true or false question is if 2 matrices row reduce to the same thing, are they the same matrix? And of course they're not. After you do row operations, you can't really talk about stuff like that for this class. Okay.
I had a question also concerning the invertible matrix. So on problem 8 of our homework for 3.5, 3.6, it asked us like, it was a question saying all linear transformations from R3 to R3 that are invertible. And the correct answers were a dilation, an identity transformation, a reflection, and a rotation, whether it was about
Yep.
the x-axis or y-axis. I was kind of asking, like, why are those specific transformations invertible?
Yeah, so we can go through those one at a time. So the first, the identity matrix just multiplying by 1. How do you unmultiply by 1? Well, it didn't do anything in the first place, so it's not really something to consider. So it is invertible. One of those was a rotation, right?
Yes, it was a rotation about the y-axis.
So if you rotate something, can you unrotate something?
Yes.
Yeah, right. And one of those was a reflection. If you reflect across something, can you unreflect something?
Yes. Okay.
If you dilate, if you stretch in like the X or Y direction, can you undo that?
Yeah, simply by like
Dividing by
divide.
constant, right? Another one that this wouldn't be true for would be if we project onto something, then it is not invertible because there's so many things going to one point that you don't know where you started from there.
Okay.
Did I miss any on that list of things that you read out?
No, you got them all. Thank you.
Okay, wonderful. Okay, I see a few other questions in the chat. Matrix midterm problems. Let's see. All right. Screenshot. Oh, is that the right one? Oh no, it's not. Too big. Okay. Is this the question you were asking? So I make sure I have the right one.
Yes, yes, it is.
Okay, cool. Okay. So this one says, suppose V is a vector such that the following is consistent. Okay. Then the set of solutions must be a subspace. So
I think you need
the
the
rules-
information from above. Like in the previous parts.
Yeah, I don't think you actually do, but I'll add it in as well. Okay. So looking at this, what we have is A is 11 by 5. So it's tall and blah, blah, blah. Okay. So suppose it's consistent. Great. Must be a subspace. Okay. So there's one little trick here that you actually don't need any information about A is solutions. Solution sets are only a subspace with one condition, and that is when we're solving the homogeneous system, AX equals 0. Okay, because we're solving for AX equals B, where B is non-zero, in our solution set, we'd have something that looks like this. Right? If we're solving for a not zero B here, okay, that means we have this. And if we were to draw the solution out, it doesn't touch the origin. And as it doesn't touch the origin, it's not a subspace. Okay.
Yeah, my question is that how do I know that B isn't 0? Like,
You don't. It could be, but the question says it must be a subspace, which it could be, but it doesn't have to be. Does that make sense?
oh, okay, but if it was 0, then it would be.
Then it would be a subspace. Yeah.
Okay.
A little tricky there. that make sense?
Yes, thank you.
Cool. Someone asked for midterm 2B, problem 6, part B. This is a common one that people see a lot in different exams. Is this the right problem? Okay, I'm just going to assume it's the right problem since I haven't heard otherwise. So what we're looking for here is they give us a matrix and they say write a basis for column of A. So I'm just going to draw this out real quick because it's a very similar thing to what I did for the first exam. So we have this lovely little tree of how to solve problems for bases, okay? What a basis is it's the bare minimum you need to construct a space. So for instance, if you have a plane, the bare minimum number of vectors you need are 2 linearly independent vectors, 2 vectors that point in different directions uniquely. For a 3 space, you need 3 different vectors that not only point in different directions, but they're not all on like the same plane. If you row reduce them, you need to have 3 pivots. Okay. So in general in this class, when in doubt, if you're scared and afraid on the exam, what you do whenever you see matrix A is you put it in reduced row echelon form, and you're probably halfway there. Okay. Now, this is where we branch off. If we're looking for the basis of a column space A, we find pivot columns. Okay. And pivot columns of original A, not the row reduced version, are a basis. Okay. And we can rewrite this over here. This isn't relevant to this particular question, but if we're looking for a basis of a null space A, from here we put it to parametric vector form. And then from parametric vector form, your vectors in parametric vector form equals your basis. So if like up here, if this was my solution set, okay, a basis for my null space would be the vector 0, 1, 1. Okay, that's how you would read it from there. So now looking at this one says write a basis for the column space of A. Well, that's a pivot column and that's a pivot column. So these 2 vectors form my basis. 2, 3, 4, 7, 10, 12. Okay, simple enough. The next one says write a new basis for the column space of A so that no vector in your new basis is a scalar multiple of the vectors in the basis you wrote in part 1. Clearly show how you obtain this new basis. So you can think of this in a couple ways. Like for instance, if we're in R2 and we span the whole space, one way we can do this is with basis vectors that look like this. The span of these 2 things span all of R2. But so do these 2 vectors, right? Or maybe this vector and a vector that goes like this. Any colored pair still spans the whole space. So any pair of them is an equally valid basis, all right? In fact, for any space, you have an infinite number of bases for that space, with the single exception of the space that is just the origin, okay? So the way that I would do this is we're looking for things that aren't scalars, but what it doesn't say is it doesn't say linear combinations. So we want this new basis to be linear combinations of our original ones, where I'll call these vectors V and W, where this is V and W, okay? The easiest way to make this is to just add them once and subtract them another time, okay? And you'll get 2 vectors that are still independent because you cannot get one from the other. There's no way you can get between them by multiplying or adding, by multiplying them since there's only 2 vectors. So this gives me a new basis of 9, 13, 16. And minus 5, minus 7, minus 8. Okay, here's a new basis. These two bases are equally valid for the exact same space. Okay, and it doesn't have to just be something like this. This could be 4v plus 10w and then 9v minus pi w, whatever. It doesn't matter. You just need two different linear combinations. And the only time this wouldn't work would be if you did like 4v plus 8w and minus 8v minus 16w. Because what you've really done is you've just written the same thing twice by scalar multiples, right?
So does it span R2 because there's like two vectors in the basis? Is that
So
how
you
we
can
know?
double check that it'll
What did you say?
span, because if you row reduce any pair, you'll get two vectors. Or another way that you can check that it's valid is if we're just looking at it without any numbers. We're looking at it as the set of v plus w, v minus w, given that we started with v and w being independent, okay? Because the basis is constructed of independent vectors, which are this one and this one, right? So looking at these two vectors that are independent, will the combinations of adding and subtracting them also be independent? The answer is yes. You can check this in a number of ways. One way you can think about it is we start with v plus w. Now the question is, can we get v minus w from here? Well, we only have one vector, so we can only multiply by a constant. Is there any way to get from here to here by multiplying by a constant? No. Another way you could see this that may make more sense. So we set V to be just a general matrix and W to be the other unit. Or I said general matrix. To make them easy unit vectors, you can see that once we combine these two things, that very clearly they still are independent. When we started with 1, 0, 0, 0, 1, 0, now we still have two things that span the exact same space. You have the same number of pivots. Okay. Does that make sense?
Yes, thank you.
Cool. So again, if you didn't get much of that, that's fine. You just need to write C1, V1. You just need to write some number times V plus some number times W, and then some number times V, some other number times V plus some other number times W. Okay, and it'll spit you out a few numbers.
Would you just explain, because I know you just explained that is how
you're pretty muffled. Can you say that again?
Yes, I know you just explained how you got 9, 13, and 16. Would you just show the numbers you used for that?
Yeah, so this is just adding V plus W, which are these two vectors up here. V and W, okay? And this one is just V minus W, okay? That's all they are. That's all those numbers represent. Does that make sense?
Yeah, so that's a lot easier than I thought it was, actually.
Right, it's a lot of words that say a lot of high level stuff that you just add and subtract.
Got you. Okay, that's beautiful. Thank you.
Yep. All right. For the next one, it says find a non-zero vector that satisfies Ax equals 0. This is the same thing as finding a vector in the null space. So we have been blessed in that they have already given us it in reduced to echelon form. So we have x1 equals minus 3x2 plus 7x3. x2 equals x2. x3 equals x3. x4 equals 0. Okay, if we augment this with zeros, right? Solve for the null space. So this gives us x equals minus 3, 1, 0, 0 times x2 plus x3 times 7, 0, 1, 0. Okay, so these two things construct my basis for the null space. So if these two things construct my basis, then we have to find a vector in here, which are just any combination of these two vectors. One combination is minus 3, 1, 0, 0. A different combination is 7, 0, 1, 0. Another combination is 4, 1, 1, 0. A different combination is minus 10, 1, minus 1, 0. These are all equally valid answers that are in your null space, okay? It's just combination of this plus a combination of this. Or just one of them, because 0 times one of them and 1 times the other one is an equally valid answer. Does that make sense? Any questions on any of this?
Wait, so for the third one, you put it in parametric vector form, and what else? What was the second step?
I just found the null space, and then so knowing that the null space is constructed of these two vectors, right? To find something in the null space, something that satisfies ax equals 0, we just find a combination of our two bases vectors, right? So this can be 1 times this one plus 0 times this one, or 1 times that one and 10 times that one, or 41 times the first one and 10 times the second one, or 41 and minus 10 times the second one. Any combination of those two. But don't make life hard if you don't need to, right? 1 times 1, 0 times the other, or 1 times 1, 1 times the other. Cool?
So when it comes down to showing work,
huh?
no, I was just saying when it comes down to showing work on that, all we need to do is just show that we got it to parametric form, and then just choose one of the
yeah, the
null
advice
space.
I give for that is if you can skip steps, that's great. But if you make some incorrect step, we can't give you partial credit, because if it's just numbers, we don't know if you actually knew what you were doing. So the more work, the better is usually the rule of thumb for this sort of stuff.
I see.
I had another question. So how do you know like when it's asking you to like put it into like parametric vector form, and then like I got like how you got the answer, but like when if you just see like the part 3, how do you know like initially to put like that you start off by putting it in like parametric vector
It's because
form?
what I see is find one vector that satisfies this, which I know is an equivalent statement to find a vector in the null space. And to find a vector in the null space, we can just find the basis for the null space and make a combination of it.
Okay.
Cool?
Mm-hmm.
All right. Let me look at some of these other chat problems. There's a lot in here, so unfortunately, I'm not going to be able to get to all of them, but I see. Okay, I see 2A, problem 7A. Let me get there.
So I just had like one quick question for the third.
Yeah, what's up?
For the third question, the last one you did, it says one non-zero vector. Could it be any of those 4?
It could be any of those 4.
Oh, okay.
All of them are the same amount of right.
Okay.
Make sense?
How did you get 4110?
How did I get 4110? I took, I missed. No, I just added them together. -3 plus 7 for my first entry, 1 plus 0 for my second, 0 plus 1 for my third, 0 plus 0 for my fourth.
Thank you.
Yep. Okay. Alrighty. This one is a headache, but that's all right. So find all values of a and b such that a squared equals a. So a squared equals a is the same as a times a equals a. Oh, that's not a. A times a equals a, right? So it gives me 4, -1, a and b. I'll make that a more clear a. Times 4, -1, a and b is equal to 4, -1, a and b. Okay. So let's matrix multiply these out. The way I like to matrix multiply is I like to rewrite my first one. And I like to write the second one that I'm multiplying above it so that they're touching corners. Okay. And now I build my bridges, which go like this. And what this is what I'm doing. I'm going to draw another matrix that fills in the spots here. And for each of my entries down here, what they're going to be is they're going to be the rows and columns that line up with it. So like this entry here lines up with this and this, okay? So how do we actually get numbers? Well, we take the rows and the columns that line up and we follow our bridges. So the first one would be 4 times 4, which is 16, plus a times -1, so minus a. Okay. For this one down here, it's going to be -1 times +4 plus -1 times +b. And in the top right, we're going to get 4a plus a times b. In the bottom right, we're going to get minus a plus b squared. Okay, this is how you matrix multiply in general, all right?
That method
So,
is revolutionary.
I would like to credit my high school pre-calculus teacher.
Wow.
She was a gem, and this method still sticks with me this many
This
years
is
later.
great.
So
Thank you.
it's quite wonderful. It makes much more sense than trying to do all the dot product shenanigans, whatever it is. So
Indeed.
yeah, I like this a lot.
People's minds.
Hmm?
I was just saying that you blew multiple people's minds with that. That was
Okay.
a very valuable method.
Yeah, linear algebra isn't as hard as you probably think it is. I promise. It's a fun topic that is extremely applicable in a lot of different fields all the time. Oh, no, stop. Okay. Okay, so now what we have is we have we have 16, minus a, minus 4 minus b, 4a plus ab, minus a plus b squared. This is a times a, is just equal to a. And let's solve for whichever of these is easiest. So I'm going to start with 16 minus a equals 4. That gives me a is equal to 12. And I'm going to solve this bottom one here for b. Minus 4 minus b is equal to -1. That tells me b is equal to -3. And boom, we are done. Don't trouble yourself with double checking everything. If you want to, you can, but meh. Cool. Any other questions about this one?
You kind of lost me there. What did you just do to compare those?
So since these two things are equal, I'm looking at this is equal to this, this is equal to this is equal to this, and this is equal to this. Because they're the same, they're equal, they're the same matrix, right? So I'm just picking whichever color looks easiest for me to solve. Which I like the red one and I like the green one, but you can solve any of them and get the exact same thing.
I see. So you're
Does
just
that make
really
sense?
looking for the easiest to find A and B through
Yep.
just simple math. Okay, got you.
For instance, we could do the blue one, which would get us 4a plus ab is equal to a. Factor an a out of everything. 4 plus b is equal to 1. B has to be equal to -3. It's all the same thing, I promise. If we've done it right, it should all be the same thing.
Sounds good. That's
Okay.
awesome.
Cool. Any other questions on this one? Right. No, there's so many things. I lost track of where I was. A7B. I think someone asked for 2A7B, which I believe I saw. So I'll refer you to the video for that one. B3, B. Oh wait, that's spring 23. I apologize. 7BII. Oh, these are both spring 23. I'm going to skip those for right now just because I have the other ones pulled up. And please specify which midterm you're referring to, A or B, for those of you that are asking questions in here as well. So I see, I'll get back to you, Francesca, for that one in a moment. But I see shot A. So mid 2B, 4A. Yeah. 200 times. Come on. Insert file. Desktop. Screenshot. Alrighty, this is a common question that confuses a lot of students. And I apologize for not responding to your email sooner. I had a very busy day. But looking at this, two things. One, null space is the line y equals x in R2, and whose matrix transformation has the range equal to the z-axis. Okay, so this null space is in R2. The range, or the same thing as the column space, okay, is in R3. So that tells me I have a 3 by 2 matrix. All right. And if the range is equal to the z-axis, that tells me that I must only be consistent for things that look like this, right? With some number in the bottom. So it tells me all 4 of these are 0. And we don't know what the bottom 2 numbers are yet, okay? So since it's the z-axis, it has to be only consistent when we're solving for z's, or you can think of it as each column has to be on the z-axis as well. And to be on the z-axis, to have x equals 0 and y equals 0, z equals something. Okay. Now solving for the null space stuff, we have x equals y. You swap x minus y equals 0. You can rewrite that out as 1, 1 for my rows. Oh, sorry, 1 minus 1. So if all of my rows must have this form, then I can write this as positive 4, negative 4. Or I can write it as 0, 0, 0, 0, 1, negative 1. Or I can write this as 0, 0, 0, 0, pi, negative pi, right? These are all the same thing that are equally valid. Any questions on this one?
So
Yes.
for the, oh, go ahead.
I was just wondering where the 1 and negative 1 came from, and if that was constant.
Where that comes from is knowing that the null space is equal to that line, y equals x, which if you want to take it a step back, x vector equals x2, 1, 1, x equals x2, which is y equals y. So from here, we write it back out, solve for 0. And from here, we get the shape of our rows. So if my first number is 0, what's negative 1 times 0? 0. Same thing here. And I just pick some random first number. It's totally arbitrary. It just matters that the first one is a number. Okay, not positive, not negative. It doesn't matter. It just can't be 0. It has to be a number that isn't 0. All right. So all of my rows just have to have this general form. So this makes it true, this makes it true, and this makes it true.
So null space line in R2 just means that there's 2 pivots and 2 columns.
Being a line in R2, a line has 1 dimension, so it's 1 free variable in 2 columns. Cool.
Yeah. That's the column space. I said instead.
The column space would be number of pivots and number of rows.
Okay.
Cool.
So I was following everything that you did to find 1 and negative 1, but now I'm questioning what if we flip it, because I see that you flipped it to x equals y,
fine.
which made y negative, but then we would just
like
have
flip
a
it like
negative
this.
x. Yeah, that's cool.
Yeah, that's totally fine.
Awesome. Okay.
All that
Why
matters is
did
whatever
you-
the first number is, the second number has to be negative 1 times that.
So you had the ones at the top of the matrix, and then you put them at the bottom of the matrix. What happened?
So what this matrix is our reduced row echelon form. Okay. So this is after we move rows around and everything, right? So this just tells me what my non-zero rows will look like. So since I know my first two rows are zeros, we know the last row is non-zero, and we fill it in with a shape that looks like this. Another way you can check this is put any of these in reduced row echelon form.
I didn't understand the second part of the question. The matrix transformation has a range equal to the z-axis in R3. What does that mean?
So range is just the same word as column space. And the z-axis just means my first two entries are 0 and my last one isn't or could be. Does that make sense? So because column space describes what my columns look like. So if they're on the z-axis, they have 0, 0, 1, or 0, 0, 10, 0, 0 something, right? 0, 0, x. Does that make sense?
Yes, but how do you know the first two are 0 again?
Since it's on the z-axis, to be on the z-axis, like think in 2D, right? If you're on the x-axis, that means your y is 0. If you're in 3D and you're on the x-axis, your y and your z are 0, right? To be on an axis means everything else is 0.
Oh, okay, thank you.
Cool. All right, one other thing I'm going to do on the note of range is I'm going to draw this little diagram I always draw, just to like tie all these things together. So I'm going to draw a couple little engineering beans. Okay. All right, and what this is this is a transformation from the domain to the codomain. All right. And what a transformation is a transformation A, okay? What it is if we take any point in here, all right, and we do A to it, okay? Generally, we do a transformation to it. It's gonna reflect like a lens to some other point, okay? And this point is my T of X, okay? And this is my X, okay? This is what the look of this is. We also see this as, this is our B, or this is our A times our X, okay? So the domain is R to the number of columns, always. That's how big this shape is. And the codomain is always R to the number of rows. Okay. So if we take every single point over here and we reflect all of them through, and they all make some space. Okay, that space will be some little thing in here. Okay. So these are all of the places all of my x's go. We call this the range, which you have also heard is your column space. Okay, and this is always number of pivots dimensional. Okay, one other important thing to note is there's another space that we need to talk about that people don't usually see in a diagram like this, but what is always in here is there is always a zero vector, the origin in each space, right? And you will always have, maybe this origin is over here. Okay, this one will always map to the origin, always, always, and forever. Okay, but there may be a few other points that also map there. Okay, where all of these pretend are going to the exact same point. Okay, what these points that all map there are is all of these, where I'll draw it so like all of this goes through this lens. Let me clean this up a little bit. All of this space, when it goes through this lens, goes just to that origin. Okay, so all of these go there. Okay, this we call our null space. Okay, and that's number of free variables, dimensional. All right, that's what all of these spaces look like. All right, where again, you have other things that are outside of the null space going to other things that aren't the origin. Cool. All right, any questions on any of this? Okay. Francesca, I will do your two problems, and then if anyone has any quick ones, we can do them after that, and then I will call it from there. So let me pull up spring 23 really quick. Oh, also one big thing to note is the majority of this exam is just asking if things are onto and one-to-one. I would refer back to some of my other midterm reviews where people have asked, we've spent almost the entire review people asking about onto and one-to-one. I'm sure you can find them in those videos. I've done it in pretty much all of my other midterm 2 reviews, and not to pawn it off, but You guys didn't ask about it, and that's totally fine. If you have more questions about it, look at it there, send me an email, post it to Piazza. So spring 23.
This is just a question about like what's going on the test. Do you think I should memorize like all types of transformations or like only like the general ones?
So the ones you really need to know are rotations, reflections, and projections, and that'll be true for the following exam as well. Just to know, like there is a math. I apologize for all of you, but you will have to remember the unit circle. That is something you have to remember for this exam. There is a simple formula for a rotation matrix. I'm sure you can find it in the slides. I'll write it as well. The rotation for counterclockwise rotation is cosine theta minus sine theta. No, I got that backwards. Minus sine theta. Yes, final answer. Yeah, and the only difference is if you're solving this for clockwise, this is going to be negative and that's going to be positive. Okay, I usually just remember one of them, and then if they actually tell me a counterclock or a clockwise rotation, I just make theta negative for those, right? This is the same thing. Rotating positive 45 degrees clockwise is negative 45 degrees counterclockwise, right? Also know which of those you can undo. You can clearly undo a rotation and a reflection. You can't undo a projection. Francesca, you asked for midterm 3B, is that correct? Or was that supposed to be 2B? To be, got it. Most of the content in it, I've taught this class for 6 semesters. The content hasn't changed between any of the midterms. So if you wanted to talk about exam 3, we can, but it's not super applicable, so that makes more sense. 7BII. 7BII. Oh, great. I'll actually tie both of these A and B together just because I think they're really good questions that really tell you if you understand this stuff. File, desktop, come on. Screen shot. All right. So someone asked about subspaces in the chat, and I know it was later than I said I would look at, but regardless, we'll talk about this one real quick. This is a very common type of question, and there's a few ways you can look at it. You can look at it graphically, or you can look at it algebraically. Graphically, what does x times y greater than equal to 0 look like? Well, it looks like all of this, and it looks like all of this. So these are the two spaces that it contains. I'll make this difficult. Okay. So it's when either x and y are both negative or both positive. And it also contains the x's. Okay. So does it contain the 0 vector? If I plug in 0 times 0, is this condition true? Yes. Is it closed under addition? What that means is, are there any two vectors in this space that I can add together that get me out of this space? And yeah, sure. I can add these two green vectors I just drew together, get something that looks like this. And boom, I'm out of the space. I've added two things that were in the space and gotten outside. So therefore, it is not closed under addition. Okay. Is it closed under scalar multiplication? If I have any vector that's in either of these spaces and I multiply it by any number, will I remain in the space? Well, thankfully the other way is still covered, and so is infinitely that way. So this would be an example where it is closed under multiplication, but not addition, okay? And what another way that you can write these in like transformation speak is the transformation of u plus the transformation of v is equal to the transformation of u plus v. That's closed under addition, okay? So this is saying if u and v are in the space, is there sums transformation in the space as well? In this case, it's no. Closed interscalar multiplication is T of C times V equal to C times T times V. Okay, doesn't matter if you multiply before or after, and it shouldn't if it stays in the space. Okay.
So really quickly, when would something be closed under addition?
Closed under addition, a different example of that would be, let me erase all this. What if instead it told you x, y is equal to 0? Okay, well, graphically, what does this look like? Looks like the y-axis and the x-axis, okay? Oh, this isn't closed under addition. Let me write this as x comma y greater than equal to 0. Okay, each of them are greater than equal to 0. When we draw this space, it is just the first quadrant, okay? So if I take any vector and add any other vector in any direction, there's no way that we can go negative this way or negative this way, so we can't escape the space. So this would be closed under addition. This would not be closed under multiplication, because as soon as we multiplied by negatives, we'd be outside of the space.
Okay, thank you.
So it may help to draw whatever the thing they're asking for is, and then you can kind of see it from there. Otherwise, you can do the rigorous algebraic way. So, looking at this, consider the subspace given this. Well, immediately when I'm looking at this, I notice this. And what does this look like? This looks a hell of a lot like a null space to me. Okay, something equal to 0. That screams null space. Something equal to 0. So how do we find the basis for a subspace which is a null space? So let's put it in parametric vector form. So our matrix is 1, minus 5, 6. Okay. So that gives me my x vector is equal to x2, 5, 1, 0, plus x3, negative 6, 0, 1. I'm just skipping the steps, but y'all know how to do this at this point. So the basis would be 5, 1, 0, negative 6, 0, 1. Cool. Another way you can technically do this is you know that it will have these two numbers be, or these two sets be true. So you can just plug them in and find out what the last number has to be. If that didn't make immediate sense, don't dwell on it. Focus on this and you'll be right. Okay. Any questions about part B1?
Yes, would you go over the I was following until you just turned them into that kind of parametric looking
So I lost you here, or I lost you here?
The first here.
1.
Oh, yes, 1.
Got it. So all I'm doing is I'm taking this matrix and I'm putting it in parametric vector form. So x1 minus 5x2 plus 6x3, which is redundant in this case, but that's okay, equals 0. x1 equals 5x2 minus 6x3, 1x2, 1x3. And there are my vectors. Cool?
Okay.
Cool. So we found the basis. The next part says, is there any matrix such that column space is equal to W? So what this is really saying is make basis of make basis the same is what this is. Okay. Well, since these matrices are a basis, we know they're independent.
Make what basis? What basis?
The basis of the column space of A and the columns and the subspace W. So the basis of both of them need to be the same for them to be the same space. Does that make sense?
Yeah.
So this is right, like basis equals basis. They have to be the same thing for them to be the same space. Okay. Well, the easiest way to do that is we know they're independent. So we just need our pivot columns to be forms of these two vectors. So an easy case, 5, 1, 0, 6, 0, 1. And boom, we have a matrix with our pivot columns being the same that form the basis for our null space we talked about in the last one.
Is this the same as the other question that we could like multiply it and add it and we would get two vectors? Like, is it the same like concept?
You could, yes. It is the exact same concept. So we just need these two vectors to be independent combinations of these two vectors. Okay. The easiest case is to do 1 times 1, 0 times the other, and 0 times 1, 1 times the other. Cool? So technically,
yes.
another way we could do this would be 11, 1, 1, and minus 1, 1, minus 1. Still equally valid, still the same basis. Totally different matrix, but the column space of each are actually equal. Okay, the matrices aren't equal. They don't give the same null space, but they do give us the same basis for the column space, which is what this question cares about.
Wait,
Just
that
focus on this.
6 would be negative, right?
Oh, you're so
That
right. You're
6
so
would
right.
be
So
negative,
that's
right?
negative.
Okay.
This would be, yeah. So these constants are off, but so it'll be -1, and this would be 11 instead. But you get the gist. I apologize.
So basically, that part 2 is just telling us to set the null space equal to column space, but since it's in
saying
the
to make sure the basis is the same. And to make
yeah,
the basis of a column space, you just make those vectors your columns.
okay.
If it were instead to be the null space of A is equal to W, well, that's a headache. But that's fine. That's actually easy because it's just this, right? We found a null, so it's asking if the null is equal to a null. It's just this. It would just be, that's an eraser. It would just be this in that case. Don't dwell on that. That's a little bit higher level, and that's not something that they would ask you. It's kind of a trick question. Okay.
Is there ever a scenario where like it says if your answer is not justified where there's no such matrix A, like in this kind of scenario, does that exist?
Let me think for a second. As long as W is a subspace, you can rewrite it as any other kind of subspace, okay? So since W is a subspace, you can write it as a column space, which is also a subspace, all right? There's different ways we talk about, there are different contexts we talk about vectors and matrices, okay? Does that make sense?
Yeah, thank you.
So long as W has a basis, so long as W is a subspace, no, there's no way that you can not make them the same somehow.
So I know you were talking about how this problem is like a good understanding of like how well you know the material or not. And my question is the reason that we can set these things equal to each other is because they're basis.
So the reason to say that they're equal is to say they have the same basis. And that is how we can find a matrix that describes it the same way. Okay, to say two spaces are equal is to say they have the same basis, or the span of the basis is the same, okay?
Okay, I understand. Thank you.
Cool, yeah. All right, last one. Write a matrix such that the column space is the span of this, and the null space is a line in R2. Blah, blah, blah. This is a line in R3. Oh, that is not R3. And this is a line in R2. So that tells me I have a 3 by 2 matrix, right? R3, R2. Okay. So let's start with the easy one. Column space is the span of that. So all of my columns must have 1, 0, 1 times. So this is a number and this is a number. The second one is 1, 0, 1. But this is some other number, right? Every column must have that form. It could be 404, it can be 505, it can be 10010, it can be 100 100. Okay, it just needs to have the same number in the top and bottom. And that's because the column space, what the columns look like are all 1 times a number, 0 times a number, 1 times a number. So that tells us about our columns. We have a pretty full matrix as it is. We would get pretty close. But now we need to talk about the null space. So if x1 over 3 is equal to x2. Does this look like how we normally like to solve these problems? No. What do we usually like? Well, we usually like x1 equals 3x2. And x2 equals x2. We can go from here. Okay. So from these equations, we go from x1 minus 3x2 equals 0, which tells me my rows all have the form of 1, -3. Okay. And notice when I do this, I always draw the matrix without a bottom tail. That's because we don't know how tall the matrix is. We only know what one of the rows, what the non-zero rows look like. Okay. So that's why I always write it with that notation. I promise I'm not messing it up. That is intentional. So that tells me I can rewrite this as minus 3a minus 3a. Okay. And what is true about this is whenever I write this, you'll always notice we always have one thing left, is because the null space and the column space aren't changed when we multiply by a number. So this is the same thing as a times 1, 0, 1 minus 3, 0, minus 3. Okay. Whatever number a you pick, it will not change the column or null space. Okay, because that's multiplying everything by a constant. So to make life easy, let's call a 1. This gives me my matrix 1, 0, 1, minus 3, 0, minus 3. Another equally valid answer would be a is equal to minus 5. This gives me minus 5, 0, minus 5, 15, 0, 15. Equally valid answer. Stick to the easy ones. I've had to correct graders and tell them that they don't know what they're doing, because students give an answer that looks like this and it is still right, which is unfortunate on the grader's part, but if that's a problem, just submit a regrade request and someone will look at it.
Would you explain the relationship between why there's just 3, specifically 3, and that's because on that x1 equals 3x squared?
Yeah, that's right here. So we don't like this. We like x1 equals. So we rewrite it as x1 equals. And then we go back to our equations, and then we have our form of our rows from our null space. Does that make sense?
Yes, that does.
Wonderful. All right. Any other quick questions before we go? You should expect the same format as you've seen on all of the previous exams as well. Couple pages true or false, couple pages true, short answer, possible, impossible, maybe provide an example. And then for this, I would probably say you're going to have a matrix where you're expected to give a column space and null space. You're probably going to have to describe some transformations, stuff like that. Maddie, if you want to email me that, I can try to get to it at some point. But I would just post on Piazza if you have questions about it as well. Okay, any other quick questions?
Just like in general, if I get asked, like if something is a subspace in R something, like what are the steps, what I should do?
3 rules for subspaces. Number 1, does it contain 0? If you plug in 0, is it true? Number 2, is it closed under addition? If I have 2 different things that are in the space, if I add them, are they still in the space? Okay. Part 3, if closed under multiplication, if I have something that is in the space, if I multiply it by any number, does it remain in the space? Okay. An example of that would be like given xy, that xy is equal to 0. If we multiply this by a number, we get cx and cy, which gives me cx times cy, and we're asking if this is equal to 0. We get c squared xy, where we know that xy is equal to 0 already. So will the c change this at all? No. That's why it would be closed under multiplication, because this doesn't change the fact that this is already 0. Okay. So that's what that would look like. Those are the big 3 things. Those are the only 3 things. Those are the 3 big rules. All right. Any other quick little questions? All righty. Good luck on your exam tomorrow.
Thank
If you
you.
have any other questions, post them.
Thank you.
Email me, whatever. I'm not gonna have my office hours tomorrow since I'm out of town. But y'all be fine. Just take some deep breaths. Know what onto and 101 are, how to find them. Know what your transformations are. If you understand all this stuff, you'll be good. So have a good night and good luck.
Thank you, Zach.